Okay, so we're going to do a problem with non-uniform velocity. This is a complication because, remember, we have three main tools to simplify the Reynolds transport theorem, and that is choosing our control volume such that the fluid enters or leaves perpendicular to the control volume, but then also assuming uniform flow and assuming density is equal to a constant so that we can pull them out of the integral and not have to do the integral. The integral over an area just becomes the area, and we can multiply the area by the velocity of the jet by density and get the mass flux across the surface. So here we're not going to be able to do that because we're going to have a non-uniform velocity. So I want to know what is the rate of mass increase in the container, and what tool do we have that lets us calculate mass accumulation given velocity profiles? Well, certainly not Bernoulli's, right? Bernoulli's assumes a single scalar velocity. So we're going to have to use conservation of mass, right? So let's write out conservation of mass. Conservation of mass, COM, says that 0 is equal to d dt integral over our control volume of rho dv. So we're integrating over our control volume the density and then taking the rate of change of that with time, plus the integral over our control surface of density velocity dotted into the unit normal of the control surface dA. Okay, so what are we going to assume? Well, we're going to assume density is equal to a constant. We call that A, which allows us, we're going to label this, to pull the density outside of our integral, right? We already know that this quantity here is the rate of change of mass in our container. So this is m dot, and this is what we're looking for. So let's simplify this a little bit. We know that we now know that negative m dot is equal to rho times the integral over our control surface of v dot n hat dA. All right, so now we want to simplify this even farther, right? And we still have a dot product, and we still haven't defined our control volume. So let's define our control volume, and I'm going to define it this way. Flat across here, down and around. So our unit normal on our control volume is pointing up, and our fluid is coming straight down, which means that they are perpendicular to they're parallel to each other, which means that our dot product is just equal to plus or minus times our velocity. And if you remember from our mnemonic from the last lecture, fluid is entering our control volume, so it is a negative value. So we can rewrite this as rho times our integral over our control surface of negative v as a function of x times, and we have unit depth, v as a function of x dA. The next thing we have to do is we have to figure out what our differential area is that we're going to integrate over, right? In this case, our problem extends into the page. It says right here, depth b into the page, like this, right? And we have a fluid flowing down our surface, coming down like this across our surface, and it extends into the page depth b. So if nothing changes into the page, it's only changing in the x direction, not the z, we don't have to integrate over that. So we don't have to do a double integral, we just have to do a single integral. So our dA becomes a b times dx. So if we rewrite this again, we get negative m dot is equal to rho integral of v of x, negative v of x, times b dx. And now we have to give our integral limits of integration, which I did not give you in the problem, so I will tell you right now. So this has a thickness of h. So we are going to integrate from 0 to h of, and then if we rewrite this again, is equal to rho integral from 0 to h of v naught over h squared times 2h times x minus x squared j hat. Well, but we've taken the dot product, so the vector goes away. And then b dx. We can do this integral. This integral is really easy. Negative m dot is equal to rho times, well, we're going to pull the negative sign outside. There's a negative sign there. Negative rho times 6 v naught over h squared times h x squared minus 1/3 x cubed evaluated from 0 to h, which if we plug in 0, we don't even need to have to worry about it. So we find out these negative signs cancel each other. Our m dot is equal to, if we simplify it a bit, 2/3 rho. I don't know why I did that. Rho times b v naught times h. Sorry, my b's look a lot like my 6's, which is why I was complaining to myself. B v naught times h. So we've solved for our m dot. We know that our fluid is entering, and it turns out this is a positive quantity, so our m dot is positive, which is great. It's exactly what we would expect. So, as a bonus problem, let's calculate the shear stress on the wall. All right, we know how to do this. In this case, it's going to be the shear stress in the x face in the y direction, which is equal to mu dv dx, evaluated at the wall, so at x is equal to, at x is equal to 0, yep, which is equal to mu times d dx of v, but we know that v here is equal to v naught over h squared times 2hx minus x squared, evaluated at x is equal to 0. So our tau xy is equal to mu v naught over h squared 2h minus 2x, evaluated at x is equal to 0, which means this goes away, and we find out that our tau xy is equal to mu times 2 v naught over h, which is twice as much as a linear velocity profile, right? Which is kind of interesting. But the reason for this is, by the way, is that if you have fluid flowing down a wall like this, the wall has to support all of the weight of the fluid. The fluid is not free falling, it's not accelerating. We have a steady state situation, so the wall has to support all of the weight instead of there being two walls like there was before. So as a result, we end up getting twice the amount of shear stresses as opposed to a linear velocity profile. Cool. So if you've been paying attention, you might have noticed that our carts that we drew a couple lectures ago, here it is. Our carts have wheels, which means that our cart can move, and if we draw our control volume around our cart, we're going to want our control volume to move as well. So what happens if our control volume moves relative to our coordinate system? What changes? Well, when we're integrating here, we're integrating over control volume of b rho. Well, what actually changes is this right here. Sorry, not v. What changes our definition of b. V doesn't change because v is relative to our control volume, right? V is always relative to our control volume surface. It has to be in order to help us calculate the mass rate crossing the control volume surface. This is going to become important later, but we have to change how we define B. So if B is equal to velocity, like it is when we're worried about momentum, we're going to, and this is obviously a preview for the next section where we talk about conservation of momentum. But instead of using V, we're going to talk about W, where W is equal to V minus the velocity of the control volume. Okay? So when would you use this, right? You'd use this if we have a cart, let's say, like this, put little wheels on it. Oops, not little wheels on it. And let's say this cart has a jet going into it, like this, where we have some V-jet and A-jet. And the mass inside this cart is accumulating with time, but the cart can move with some V-cart, which is also a function of time, right? So this becomes really important if your cart is moving, because obviously if your cart is moving faster than your jet of liquid, then it's not actually going to accumulate any mass or momentum due to the jet, right? It's moving faster than the jet. The jet's just not even keeping up with it. So it becomes important to be able to talk about the relative velocity of the jet and the CV. So we're going to rewrite our Reynolds transport equation as the total derivative of some quantity b is equal to d dt of rho b dv plus integral of the control surface, sorry, this is integral of the control volume, of rho b w dot n hat dA. Just to make it absolutely clear that this is the velocity relative to the control volume surface. Okay? So from now on, we're going to write this velocity as w, and then if velocity shows up somewhere else, we'll write it as v. But we want to make sure those two are absolutely separate. So, quick review of steps and tips for solving Reynolds transport theorem problems. 1, always draw a control volume. This is not an option. 2, draw a smart control volume, right? You won't always be able to do this, but as much as possible, you want to be able to draw the control volume perpendicular to the velocity of the fluid. All right? We want to find our velocity relative to our control volume. Do the dot product. Hopefully it's easy. And then integrate. Hopefully we can assume density is equal to a constant or uniform velocity. And after that, done. We've solved the problem and we can win. Good deal.